can hear me? Am I audible? So we will discuss electric traction in very brief because itself traction is a subject. So it involves whatever you have studied till now. That it involves power system, it involves motors, drives, protection, measurement, everything. So it is by itself a subject. It is a particular application of it is a wide application of the electrical engineering. So basically, this is the first, that is just the introduction of traction system. That is, electric traction system was introduced long back in 1888. That is, the electric traction system vehicles draw energy from the distribution system from a control wire suspended over the track or from a parallel rail running parallel to the track, that is the third rail. Now, in our railway system, we have that wire. Also for tram, we have the trolley wire suspended over the track. However, in our metro and most of the metro rail system where we have got underground, then we have the third rail. Because if we want to have the trolley, then the height of the tunnel becomes very large. So, but however, due to its flexibility, the trolley wire is far better option than the fixed third rail. But obviously, for metro system, we have to go for the third rail. Now, why the traction system has shifted to electrical? Because when first introduced the railway, we had the steam engines. Then came the diesel engines. Then obviously, most of all developed countries, they have electric. All the tracks in our country, most of the tracks now becomes electrified. Very little, might be very little stress we can have diesel engines. Steam engines are no longer used, coal-fired steam engines. So the first advantage is that the cleanliness. The electric generation itself creates pollution, but that is concentrated at the place of generation. So when the rail is the train is running over the track, there is no pollution. It is pollutionless. But consider the steam engine; it will create lots of pollution over as it is running. Then the electric drives have better speed control. So as the speed control, braking, both are better, so we can go for a higher speed. The average speed is for the vehicle is much higher. Electric drives have rapid acceleration and retardation, hence the scheduled speed is much higher. Then the coefficient of addition is better. These terms we will define for the traction system. So coefficient of addition is better because the torque of electric motor is continuous. And this continuous motor and the distribution of driving wheels along the length of the train. Whereas for the steam engines and the diesel engine, basically the engine was pulling the entire vehicle behind. So their addition was less. So when addition is better, then we can attain a higher speed without sleeping. So the locomotive also results in improvement in riding quality and reduction in wear and tear of the track. The electric locomotive can put into service immediately. There is no warm-up period because for the steam engine, if we consider the steam engines, then before starting the vehicle, the engine has to be ignited some almost 2 hours for warming up. The steers furnace will be operating, then steam will be generated, then only the machine will operate. Though our diesel engine do not have that large warm up period, but it will have pollution. The electric energy required for light and fans of the vehicle can be drawn from the line itself. For diesel and steam engines, there has to be axle generator for the light and fans, that is no longer required. Then electric braking is superior to mechanical braking because of less wear of brake shoes, wheels and tracks. In case of regenerative braking, a part of the energy is returned to the supply. That is, some energy we can retrieve during braking if we are going for electric braking. A disadvantage mainly means that electric traction system involves heavy initial cost because of the extensive power supply that has to be created. Then failure of power supply for a few minutes will stall the whole system. The electric traction system is tied to the electrified room. Unless electricity is there, we cannot go for electric traction system. Now, this is the just general discussion. Then we will, as I have told, that the traction itself is a subject, so we will define few terms related to the traction system and few devices used. Now, first is the speed time curve. The speed time curve is the movement of the train and their energy consumption can be most conveniently studied by means of the speed time curve. Speed time curve from this is basically a plot like this, a plot between time and the speed over for the train, that is for two successive stops. Now these are different portions. It is divided into different portions. This portion OA, it is called the notching up period. Now this curve has been explained in term considering a series motor with rheostatic starting, but this is easier to explain. However, for other types of traction machines also basic idea is the same. Now for this region, when the machine is starting, we have a resistance which is varied. The resistance is varied and the resistance is such design that the current is limited within a specified value. So gradually the motor accelerates from speed 0 to say at this point. Now at this point there is no more resistance in the circuit. So resistance is not there, then that motor, that the characteristic of the motor will now follow that series characteristic, inverse characteristic like this. Initially for starting it is approximately constant torque because we have controlled the resistance in the circuit. Now the resistance is no longer, external resistance is there, so it will follow the inverse characteristic of traction drive. So this is the motor torque developed. It is the called the tractive effect. Now you can, and this is the load torque, the traction train resistance. The train resistance corresponding different values we will discuss. So that is basically the load torque characteristic. For traction drive it will be something like this. That is the initially when the motor starts from rest, for initially at very low speed, the torque requirement is quite large because of the friction or the large static friction. because it is a long vehicle, so it will have large inertia and large static friction. Once that static friction is overcome, then then it will gradually reduce. Gradually, it will turn like this. So the characteristic is like this. So at this point, these two are equal. So this is the operating point. So in between, this still the motor torque is more than the load torque. So the vehicle will still accelerate, but the slope will be slightly different, slightly less. Then at here it has attained the maximum speed. So now it will run at that constant speed unless there is some disturbance for certain time period. Now the vehicle has to stop at the next stop, and that should be precisely at this point. So normally this portion, this is called coasting. That is, it is not braked, but what is done, the supply is cut off. The motor supply is cut off, but the vehicle will run and slightly retard because of the inertia of the whole system. It will have a large inertia, so it will go on running, but the speed will drop slightly. Then once the speed has dropped to this point, then the braking is applied, and it is quickly comes to rest at this point. So this is the ideal speed torque curve. Now this is kilometer per hour, this is time. So area under the speed torque curve will give the distance traveled by the train. So this is the ideal case. Now depending on which application we are going for, the urban, suburban and long distance, that curve, which portion will be larger and which portion will be smaller, that will differ. So we have for that notching up period, speed curve running or acceleration of speed curve. This is AB portion. Then constant speed running, free run BC. Then coasting. This portion is called coasting, where while we cut off the supply. Now this coasting you can very easily understood for the local trains. You can see for always there is a small time span where the fans and lights goes off, but the train goes on running. That is for the coasting operation, because the fans and lights will go off because the supply is cut off, but the machine will run. So some energy is saved for that. The coasting is an important operation for application, that is say for this was the ideal speed torque curve we require. Now say from between point B to C, the machine will run at a constant speed provided there is no disturbance. For say there was some disturbance, so the machine has to slow down. Then again it speeds up, so again it will follow this curve. So if we find the distance traveled, this distance is lost. So during the coasting period, they can this coasting period, this can be made longer, for because we are considering the effect depending on the same energy spent. So we can increase the coasting period, and for the same energy input, we can have the same distance covered. So suppose there is a small irregularity in the line and the train is forced to slow down for some losing some distance, that is this portion. To make up for the distance, the train starts coasting at point C. As a result, this portion of the area is gained. Otherwise, if we break the machine, then the braking curve will be like this. It will come like this. So this area here is retrieved. Now speed time curve, as I told, we can have typical speed time curve can be divided in urban or city service, suburban service, and the mainline service. Urban, this depends on what is the locality through which the line is running and the distance between the line. Urban service, the distance between the two stops is very short, 1 kilometer or so, say for the metro rail or the circular rail service what we have. The time required for this run is very small because the distance is small, so total time between the two stops is quite small. The acceleration as well as retardation is required to be high so that the high average speed and the short time of run is obtained. The acceleration and retardation for urban service is 1.5 and 4 kilometer per hour per second, and they are between 3 and 4 kilometer per hour per second. Now note the units. These are the typical units used in traction system. That is the acceleration. Normally, what we will have meter per second square or kilometer per second square here, kilometer per hour per second. This way it is expressed. That is a normal expression. So free run is not present in this run because so the characteristic will be, that is, it will accelerate, then there will be a long posting period, then braking. This will be typical urban service torque speed curve. Speed time curve. The posting period is small, typical speed time curve or the urban service is shown. Then the suburban service. In this service, the distance between the stops is little larger than the urban service. So between 1 to 8 kilometer, free run is still not possible, but posting region is comparatively longer. Acceleration retardation required are high as per the urban service. That is, these two are almost similar, but for urban service, this distance is very small. So there is a posting, but not very long. But here, the suburban service, there is no continuous running, but there will be long posting period that saves energy and cost. Mainline service, obviously, we will have a very long continuous running, and the posting will be small compared to the other portions. So for mainline service, that mainline service, this continuous running is long. So this acceleration posting portion is comparatively smaller. So mainline service, the speed time curve is approximated by this trapezoidal, and for urban and suburban service by this curve. This one. These are approximate speed time curve. Now, so there are three types of services: urban service, acceleration per kilometer per hour per second. Acceleration value is 1.5 to 4. Retardation is 3 to 4. Maximum speed is 120 km per hour. Distance between station is 1 kilometer. The speed time curve, no free running period, small posting period. Suburban train service, again the acceleration is 1.5 to 4 km per hour per second. Retardation is 3 to 4 km per hour per second. Maximum speed is 120 km per hour. Distance between station is 1 to 8 km. There is again no free running, but there will be long posting period. Main line, Acceleration and retardation is small, 0.6 to 0.8. Retardation is 1.5. Maximum speed is 160. Might be higher depending on the type of engines we are using. Distance between station is more than 10 kilometers. So free running of 10 kilometers. So coasting period, acceleration, and braking periods are comparatively smaller than that. So we define certain values. That is the crest speed. Crest speed is the maximum speed attained by the vehicle during the run. Is known as the crest speed. Average speed will be the distance traveled between two stops. They were divided by actual time of run. That is the average speed. Now, when we go for schedule speed, there will be a stoppage time. So, for schedule speed is distance between two stops divided by actual time of run plus the stop time. From above, it is observed that the schedule speed is always smaller than the average speed. The difference is large in case of urban and suburban service and is negligible, small in case of mainline service. Because mainline service, the stoppage time will be small compared to the actual time of run. Now, factor affecting schedule speed. From the expression, you can see that factors which will affect the schedule speed will be acceleration and braking retardation. That is faster the and maximum and speed or the maximum speed and duration of stop. This will affect the schedule speed. Now, effect of acceleration and braking retardation. For a given run and with fixed maximum speed, the acceleration increase in acceleration will result in decrease in actual time of run. Therefore, increase in schedule speed. Actual time of run will decrease, so schedule speed will increase. Similarly, increase in braking retardation also affect the schedule speed. Variation in acceleration and retardation will have some effect on schedule speed in case the shorter distance run is comparison to long distance run. That is obvious because for the long distance run, the free running period is very large, so change in acceleration or retardation affect the speed very little. However, the effect of maximum speed for a constant distance run and with fixed acceleration and retardation, the actual time of run will decrease. The maximum speed increases, so schedule speed will increase with the increase in crest speed. The effect of variation in crest speed on the schedule speed is considered in case of long distance run. This is maximum in case of long distance run, the effect of the maximum speed. The effect of duration of stop, obviously if duration of stop increases, then the schedule speed will decrease. When the distance between the station is much larger and duration of actual run is long, as in case of main line, then the duration of stop has less effect on the schedule speed. So then the next simplified speed time curve, that is, as I told, that for long distance run, this acceleration time is small, so it is approximately consider this trapezoidal curve. And for short and urban and suburban operations, that constant speed running is absent. So we will consider only the acceleration, then coasting, and then retardation. These are the approximately curve. we can calculate the speed distance traveled. For the first one, that is this one, say the acceleration is alpha, retardation is beta, Vm is the maximum speed, T is the total time of run. Then time of acceleration is this time. This is maximum speed V, so Vm. So Vm by alpha is that T1, and T2 is some time of deceleration, that is this time. So Vm by beta will be T2. So the rest time of constant run will be capital T minus T1 plus T2. That is T minus Vm by alpha plus Vm by beta. So total distance of run will be distance traveled during acceleration, distance traveled during free run, distance traveled during braking. So distance traveled during acceleration, this is this trapezoidal area, this triangular area. This will be half base into altitude, half Vm into T1 by 3600. This is because of the units. Vm is kilometer per hour. So T1 should be in hour. Then Vm is equal to T2 by 3600, where T2 is T minus Vm by alpha plus Vm by beta. And again, this is the triangular portion, half Vm T3 by 3600. So the total distance is will be equal to Vm square by 7200 alpha plus Vm by 3600 T into Vm by alpha plus Vm by beta plus Vm square 7200 by beta. So if you expand, this is the expression. So this minus this and this minus this, we will have is Vm by 3600 T minus Vm square by 7200 alpha minus Vm square by 7200 beta. This can be written as Vm square by 3600 into 1 by twice alpha plus 1 by twice beta minus Vm T by 3600 plus S is equal to 0. So substituting this factor as K, we can write this as K Vm square minus Vt T 3600 S is equal to 0. So from this expression, Vm is equal to T plus minus root over of this by twice K, can be written as K square by 4K minus 3600 S by K. Now positive sign, if we put the values, we will say positive sign gives the value of Vm is very high. So neglecting that, we can get the values that Vm is equal to T by 2K minus over K square by 4K square minus 3600 by S by K. So calculation, then the quadrilateral speed time curve, that is for this urban and suburban one, this one we consider. Here acceleration is alpha, Vc is the coasting retardation, V is the braking retardation, Vn is the maximum speed at the end of acceleration, V2 is max speed at the end of coasting, T is the total time of run. So T1 is V1 by alpha, then T2 is V2 minus V1 by beta C. That is, this change is voltage, V2 minus V1 by the costing retardation beta c, and T3 is V1 by beta. So again, distance traveled will be distance traveled during acceleration plus distance traveled during coasting plus distance traveled during retardation. So putting this value, this is for this triangle. Then this for this trapezoidal, and this is for this. So putting this value and simplifying it gives a relation that S is equal to V1 by 7200 T1 plus T2 plus V2 by 7200 T2 plus T3. Putting T1 plus T2 plus T3 is equal to T, we get this expression, that is V2 is equal to V1, this one 7200S is equal to T into V1 plus V2 minus V1 V2 into 1 by alpha plus 1 by beta. Now V2 is V1 minus beta C T2, V1 is beta C into, replacing T2 by T minus T1 minus T3, so beta C into T minus V1 by alpha minus V2 by alpha. So that will give you V2 is equal to this one, V1 minus beta C T plus beta C by alpha V1 by 1 plus beta C by beta. Now when values are given, obviously putting the values, we can get the distance which is traveled. Now before going to the mechanics, I'll just have a small problem. Just simply that this is the speed time curve given, that is the Vm is the maximum speed obtained, V1 is the speed after coasting. Now this acceleration time is 30 seconds, free run is 180 seconds, coasting time is 20 seconds, and there is a stoppage time of 30 seconds, it is given, and beta retardation is 2 km per hour per second, beta 1, this is coasting retardation, 0.15 km per hour per second, and acceleration is 1.5 km per hour per second. So to find out the distance, we have to find out the distance and the schedule speed and average speed. Now Vm, that is Vm, we can find out from here. We know the acceleration, we know the time. So Vm will be 30 into 1.5 km per hour. So it will be 45 km per hour. Distance covered in 30 seconds is the this triangular area. So half base into altitude. So half 30 into, this is 45 by 3600 because of that unit. So this is 0.1875 kilometer. Now distance covered during the free run of 180 seconds will be 45 by 3600. This is the speed into 180, so 2.25 kilometer. Now V1 will be Vm minus beta 1 T. So this is Vm, that is beta 1.15, this is 20 T. So this is 42 km per hour. So distance covered in 20 seconds will be this trapezoidal area. This is Vm, this is V1. So this is 20. So this will be half Vm plus V1 into T3. So half 45 plus 42 by 3600 into 20. So this is 0.242 kilometer. Speed arrived attained at after time T4 is 0. So this time is not given. This time is not given. So that we have to find out. So here the speed is V1 and the retardation value is given. So this is 42 minus 2 into T4 T4 is 0, so T4 is 21 seconds. Now 21 second distance covered will be half into 21 into 42 by 3600, so 0.1225 kilometers. So total distance traveled will be addition of all this. So adding we get 2.802 kilometers. That is the total distance traveled. So average speed will be total distance traveled divided by actual time of run. Multiplied by this because again because of that unit. So this will be 40.18 kilometer per hour. Schedule speed will be actual distance divided by actual time of run plus the time of stop. So this will be schedule speed. So average speed and schedule speed will be different. Now the vehicle movement involves a lot of mechanics, so that mechanical details we are not going, but simply define that certain terms. It is necessary to know the train mechanics of train movement. Say this is the motor armature. It is motor is normally connected to a pinion, and the pinion is driving this gear wheel. This gear wheel itself is driving the main road wheel. So the driving motor exerts a torque T in Newton meter. So driving motor is exerting a torque T. So driving motor torque T and the pinion diameter is D dashed. So T is equal to F dash D dashed by 2. F dashed is twice T by D dashed. Now tractive effort transfer to the driving wheel. Tractive effort driving to the driving wheel. This is the gear wheel D, small d, and the road wheel is D, so capital D. So this is the force. This is the efficiency of the system. So efficiency into F dash into D by D. So it is transferred from here to this smaller wheel, then this to this. So F dash D by D. So this will be neta twice T by D dash D by D. Neta T just it is rearranged. So neta into T 2 by D D by D dash. So this is eta T 2 gamma by D, where gamma is the D by D dash. D is the diameter of the gear wheel in meters, D is the diameter of the driving wheel in meter, and neta is the efficiency of the transmission, and gamma is the gear wheel ratio equal to D by D dash. That is, this is the motor is connected to the pinion, so the torque is transferred through this combination D dash and D. This is the gear ratio. The above equation suggests that the tractive effort, this force is a tractive effort. Now from the above equation it suggests that tractive effort on a driving wheel can be increased by increasing the torque T. Now However, this is possible up to a certain point, but after that, increase in the motor torque does not increase the tractive effort, but it will tend the wheels to sleep. That is, if we go on increasing the torque for a particular type of combination of the wheels and the rail, after a certain speed, the wheels will sleep. The maximum frictional force between the driving wheel and the driving wheel and the track is say mu into W, where mu is the coefficient of defined as the coefficient of addition between the driving wheel and the track, and W is the weight of the train on the driving axle. It is called the adhesive weight. Sleeping will not take place until the tractive effort is greater than mu W. That is, for motion to sustain, the tractive effort should be less than maximum. It can be equal to mu W. So we define that this should be equal to mu into W. So we define the tractive coefficient of addition mu is equal to tractive effort to sleep divided by the adhesive weight. Now, this coefficient of addition is greater for a electric drive system. That is, because the electric, we have more than one electric motor and the driving axles are distributed throughout the total vehicle. So addition is better for electric motors. That is, adhesive weight increases. The magnitude of tractive effort that can be employed for propulsion therefore depends on the weight coming over the driving wheel and the coefficient of addition between the driving wheel and the track. Obviously, coefficient of addition also depends on the type of the track, whether it is greasy, oily or slippery. That also will affect the coefficient of addition. The coefficient of addition is defined as the ratio of tractive effort to slip the wheels and the adhesive weight. This is a table for coefficient of addition for average speed. That is, if we go on increasing the speed, coefficient of addition will be decreasing. The normal value of coefficient of addition with clean dry rail is 0.25, but with wet and greasy rail, this value is decreased to 0.02. So that is, during rainy season also there is a tendency to more slip. In order to increase tractive effort of a locomotive, so that is, it is not only sufficient to increase the rating of the motor, driving motor, but it also depends on the weight on the driving wheels will have to be increased. The adhesive weight can only be increased by increasing the number of driving axles. In steam locomotive, it is done by using coupling rod to connect the driving wheels. Addition also plays an important role in braking. If braking efforts happen to be more than the adhesive weight of the vehicles will skid. If the braking effort is too large, the vehicle will slip from the trail. That's how there are accidents if the speeds are not proper. Now, factor affecting sleep. Sleep is a very important phenomena in case of traction drive. So, what is the factor affecting? The addition is a result of meshing. Now, what is the physics behind it? Addition is it's a result of meshing of rough patches that occur even on the highly polished surface. highly polished bodies. The inner atomic forces between the protrusion of these rough patches, which result in a sort of welding between them. In practice, instead of pure steel to steel contact between rail and wheel, there are foreign materials on the surfaces, say films of inorganic matters, metallic oxide, layer of brass. It has a detrimental effect on adhesion. Various factors affecting adhesion are the condition of the track, the mechanical parts, and the electrical parts. Electrical traction has very important advantage of a steam traction, and that is on account of greater adhesive weight. In the motor coach, 100% of the weight is on the driving wheel. That is in the motor coach. Say for the local trains, the total driving motor is distributed over the whole length of the vehicle. So the for motor coach, 100% of the weight is on the driving wheel. In an electric locomotive, where we have the electric engine pulling the vehicle, it is 70%, whereas in steam locomotive, it is less than 50%. The coefficient of adhesion in electric traction is also greater than that in steam traction due to following reasons. In electric traction, the torque exerted is continuous in nature. In steam traction, the torque is pulsating, which causes jolting and skidding. In electric traction, the driving wheels are distributed over much greater length, whereas in steam traction, they are close to each other. Higher values of tractive effort can be used in electric traction, therefore, an electric train can be made to accelerate faster at a faster rate. The result is it saves time, especially when the distance between the stop is small, that is urban and suburban areas. Now, this tractive effort for propulsion of train. Now, the force that the motor generates will propel the train. Now, the train offers certain resistances to the motion. So, the total tractive efforts required to run the train can be divided into different parts, that is tractive effort required for linear and angular acceleration, that is the force exerted by the motor will create the linear acceleration of the vehicle. The vehicle should accelerate linearly. Now to impart this linear acceleration, angular acceleration should be imparted to the internal components. So both the acceleration should be both linear and angular acceleration should be imparted. So tractive effort for imparting linear and angular acceleration plus tractive effort to overcome the effect of gravity. When the train is running over a steep slope, so it has to overcome the effect of gravity. The gravitational pull, we will see that can be divided into two components. One is acting downwards and along the slope. So that is additional forces required to overcome that component. Then tractive effort to overcome the train resistance. Now train resistance is basically due to the air resistance. There are two parts. One is the end resistance and that is the compression of air at the front and the suction of air at the back, and the frictional resistance over the whole length. So that is the train resistance. So it depends obviously that as the length of the train increases, the frictional resistance over the surface increases, then the end resistances, that particular front resistance and the back resistance, that will depend on the speed. So basically, if we see the shape of the very high speed electric engine, you will see that it has very typical shape. It is called the aerodynamic shape to overcome that will reduce that train resistance. Then there is another component, tracting effort to overcome curve resistance. When the train line is not straight, curved, then as the train goes over the curved line, then the flanges and wheels will come near to each other, so there will be more friction, so that will increase the resistance. So these are the different parts of the tractive effort. So these are important, and we will just have the definition and just empirical expression of the tractive efforts that we will discuss in the next class. Next Thursday is Poila Boishakh, so I will take the next class on next Tuesday. Okay.
Yes, ma'am.